Hello. Good morning, everyone. Am I audible? No. Am I audible? Can you hear me properly?
Yes, ma'am.
Okay. Today it is clear, right? Okay. So, is my screen visible to you all?
No, ma'am.
Now?
No, ma'am. Now it's visible, ma'am.
Okay. So, in the previous, the flat slab sum, the first sum which we had done, there was what? Both, we had a question of longer span and shorter span, two problems we had done without, that was the first question was without drop and panel head. We had done till reinforcement, and then there was a shear check was also there. So, this after the calculation of the reinforcement, okay, in the flat slabs, the first, I'm taking the first question now, the first question which we had solved. So there, after the reinforcement calculation, we have to check the shear. Okay, whether your design which you have done and you have provided the reinforcement, whether it is safe or not along the shear. Okay, IS code says that if you check for sure, then it should be checked in critical sections. Okay, and I think I had said this thing in the last class maybe, but maybe the network was having issues with the network. So I think maybe it was clear or not. So let me show you once again. See, this was our column. See, according to IS code, we have to check the shear in the critical section. Okay, and so we have to find out where is our critical section so that we can check for the shear. Okay, so this was our column 400 into 300 mm in the first question. So this was the longest one, this was the shortest one. So according to IS code, it is your critical section is at a distance of 0.5 d. That means half of the effective depth. This one. Our there was, I think, correction along the shorter span, so effective depth was 165 there. So it is how much? This one 8.25. If you see here, this one 8 point, sorry, 82.5. This much is 82.5. From here again we have 82.5. That means d by 2, d by 2 this distance, d by 2 this distance. 82.5, 82.5. Now if we go to IS code page number 8, Hello. See here, calculation of shear. Okay. So also here you will see in this page number 57, shear in flat slabs. This one, shear in flat slabs. So the critical section for shear shall be at a distance of d by 2 from the periphery of the column or capital or drop panel perpendicular to the plane of the slab, where d is the effective depth of the section. Okay. This is your shear in flat slabs, that is d by 2 you will get here in this figure. Again see figure 12 this. Okay. So if you see this figure 12, sorry, yes. This one is your critical section from the column d by 2 distance. This one you can see here. And if you have this thing drop and column head also, from the column head, it is how much? That means from the capital it is d by 2. This one is your critical section here. This one here. Okay. So here if you see this one d by 2, from the figure we can see 12, we can see the what was the critical section at a distance d by 2 from the column, or the if it is column head is there, from the column head it is d by 2. Okay, now here you see calculation of shear stress. The shear stress tau v shall be the sum of the this. The nominal shear stress in flat slab shall be taken as v in by v naught into d. This one. Okay. The nominal shear stress in flat slab shall be taken as v by v naught into d. So to calculate this nominal shear, you have to know your v, which is the shear force. This one, shear force due to design load, and v naught is the periphery of the critical section, and d is the effective depth. Okay, and d is your effective depth. So to find out what is your VU, if you go here, you see here, we know we have our shear. This one, the nominal shear stress is given by V by B naught into D. So that is V by B naught into D. Okay. So what is your VU here? The shear force. Okay. Here, this is your dimension of the this thing, the panel, which was given to you 6 into 4.5. It was in your first question, the 6 into 4.5, the panel dimension sizes, minus we will do this portion. This from the panel, if we do this minus this and this, the critical section, we will get that shear force on this portion. That is 465 from where it came. See, you have this distance is 400, this is 400. So we have got our critical section to be 82.5 here. So 400 plus 82.5 plus this side 82.5. So that is your 465. Okay. And here this is your 300. This portion, this length is 300. So this is how much? Sorry. This was 500 plus 82.5 plus 82.5. So this is 565. And this is 300. 300 plus 82.5 here, and this side 82.5. We will get this one. 465, the vertical distance, 465, this one, this portion. Into our, I think this was your factored load. You can check in your first question where we had solved. There, I think this was your 15 was your factored load which you got. So from here we will get this shear force, right? This force we have calculated here, which we got it to be 401.06 kilonewton, the shear force. Now, what is your B naught? B naught, see here, what is that? B naught is the periphery of the critical section. This one, B naught is your periphery, which is nothing but this distance, this one, 2 into this, 256, 256, 2 into 465, 465. This is the periphery area. Okay, so this much, which is 2060, periphery of the critical section, and D is the effective depth. D we know, 165 we have taken here. So according to now, so we can calculate our shear stress here. VU we have got the shear force. This one 401.06 kilonewton it was, and so B naught we know we have calculated it to be 2060, and we have the effective depth 165 here. 165. So we got our shear stress to be how much? 1.18 Newton per mm square. Now we have to go to clause number 31.6.3.1. If we go to clause number 31.6.3.1, here you will see permissible shear stress. We have calculated our shear stress. Now we'll see, check whether it is permissible or not, whether that shear stress is permissible or not. For that, you see this clause 31.6.3.1. Here, what it says that when shear reinforcement is not provided, the calculated shear stress at the critical section shall not exceed Ks tau c. Okay, that means here this shear stress which we have calculated, that this Kc, right, the Kc value, that means the tau c dash, if we say tau c dash to be this Ks into tau c, if this is less than our calculated shear stress which we just had calculated here, this one, okay, if that is less, then it is not permissible, because here this design should be more. Okay, so which is, here you will see, when shear reinforcement is not provided, the calculated shear stress at the critical section shall not, the shear stress at the critical section which we just calculated, this one, shall not exceed this much. That means your shear stress which we had calculated, okay, their shear stress which we had calculated, this should not exceed our this value Ks tau c, and if it exceeds, that means shear stress is not provided, and okay, shear stress is not provided. If we see now here, uh, tau c, again one more thing. Here you will get all the values. Ks is what? Ks is this zero point 0.5 in plus beta c, but not greater than 1. Beta c being the ratio of short side to the long side of the column, or capital. And what is a tau c? Tau c is 0.5 root over fck in limit state method. Okay, so this values you already know. Okay, so let us check now whether our this shear stress is less or greater than the one which is provided to us in the clause number 31.6.3.1, that is tau c value. So if we see here, tau c value was how much? This tau c dash, we can consider it to be tau c dash. So tau c dash is ks into tau c, ks into tau c, this one. Okay, ks into tau c. Now we have to calculate what is our tau c and ks. So if we see here, what is our ks? 0.5 plus beta c, but not greater than 1. Beta c being the ratio of the short side to the long side. Okay. Now ks is what? 0.5 here plus beta c. Okay. So beta c was what? The ratio of the shorter to the longer. Okay. So This is how much. This will 300 by 400. This will be like 0.75. So this the shorter span to the longer span here. This one beta c being the ratio of the short side to the long side. So short side to the long side is how much? Our 0.75. 300 by 400 if you do it is 0.75. But here it is mentioned that beta c be but not greater than 1, being the ratio of the side, beta c being the ratio of the side to the short side to the long side of the column or capital. So we will place this 0.5 plus 0.75, we got it to be 1.25. So it is greater than 1. So we will consider it to be ks value to be 1 because it is mentioned here. This value ks is 0.5 plus beta c, but it should not be greater than, it should not be greater than 1. Okay, this beta c value should not be greater than 1. Sorry, not beta c, Ks value should not be greater than 1. So we have got 1.25, so we will consider it to be 1. Now, tau c, what is our tau c? Tau c is 0.25 FCK in the limit state method, and we know that. So 0.25 into our FCK. And what is that? 0.25 into, we know FCK is M20. So this one we have got it to be 1.11. So 1.11 is our tau c value. Now if we compare this tau value which we had calculated here, the shear stress, okay, according to our this the flat slab dimension, the column with the column, the critical section. At the critical section, this was our shear stress 1.18 Newton per meter square. This is greater than our tau c dash, which is 1.11. So this is not permissible. Okay, if this would have been, this tau c would have been greater than at the critical section, the shear stress at the critical section, then this shear stress would be permitted. And since this is not permissible now, our tau c dash, this one, our this permissible stress tau c, Ks tau c, that means which we have considered it to be tau c dash, is less than our critical, the shear stress at the critical section. So we have to, it is not permissible and we have to provide the shear reinforcement. But if our tau c dash would have been greater than the shear stress at the critical section, obviously then this is safe and we don't need any kind of shear reinforcements. Okay, so this is not permissible, so that means we have to design for shear. Okay, shear reinforcement should be provided, right? So now if I show you that next one, if we see here 2. Okay, so here now we'll come to the step number 9, that is, since it was not permissible, so we had to calculate the shear reinforcement, we had to provide the shear reinforcement. So we will consider it to be 8, 5 stirrups will take, you can take it yourself, but the shear reinforcement generally for the stirrups we take it to be 8. Okay, uh, or 6 you may take, 6 or 8. 8 we have taken here, and 8 legged FE415 rate. So here this is the shear reinforcement which you have to provide here. You see this much reinforcement we have provided, 8 mm stirrups, 8 mm dia stirrups, 8 legged. So here the shear reinforcement, if you see, it is 0.87 into F15, that is 415, sorry, into ASB into D by VUS. Okay, 1 minute. If you go to the IS post, one more thing I want to tell you. When the shear stress at the critical section exceeds the value given here, everything is mentioned to you. Okay. related to the shear reinforcement. When the shear stress in the critical section exceeds the value given in this, that is the clause which we had calculated just now. If it is when the shear stress at the critical section exceeds the value in this much, but less than 1.5 tau c, shear reinforcement shall be provided. So we have provided the shear reinforcement. Okay. If the shear stress exceeds 1.5 tau c, the flat slab shall be redesigned. Okay, got it? This one. See, we had in our the shear reinforcement which we had calculated, we have got what? It was greater. Our shear stress was greater in the critical section. It was greater than the tau c according to IS code, according to clause number 31.6.3.1. But when it is greater, we know we will provide reinforcement. But what else you have to do? If it is greater, if your tau that the shear stress is greater in the critical section than the tau c dash which we had calculated, then all this, then what happened? You have to check if it is greater, like in our question it is greater. So we have must check for 1.5 tau c value. If this 1 point tau c is less, then shear reinforcement shall be provided. And in our case also it was less. Okay, tau c was just now we had calculated the tau c dash was 1.11. So it will be less than this value. Okay, 1.5 tau c, it will be less, so we are providing the shear reinforcement. But if the shear stress exceeds 1 point tau c, then the flat slab shall be redesigned. We have to take the overall depths, etc., all this dimension. We have to change all those things, the overall depth, the reinforcements which we are taking, etc. We have to redesign everything. Okay, if your tau c your tau v is greater than tau c dash, and your this 1.5 c is greater than greater. Okay, greater if your that value exceeds this value 1.5 tau c. Okay, and here where is the, let me see, one's eccentricity. I've showed you these things. Permissible shear stress here in page number 58, 50. Okay, okay, where so here, now if we see, these are the stirrups. That means we have to provide shear reinforcement, and shear reinforcement is nothing but the stirrups will provide. Okay. Uh, when we have to provide for reinforcement, shear reinforcement, then we provide extra stirrups there for resisting the shear. Okay, after checking the shear reinforcement. Uh, Now we, since we have considered 8 mm diameter stirrups, 8-legged, so the spacing we'll see what is there for shear, that is 0.87 into uh, FE 415, that is FY 415 into ASV into D. It is given by this your spacing of the stirrups for shear. It is given by this formula 0.87 Fy into ASB into D by FBUS. So what is your ASV? It is the area of the shear, this one of the stirrups. So this one pi d square by 4, 8 legged. So it is our ASB is 402 mm square. And what is your VUS? This is your VUS given by VU minus 0.5 tau C B naught into D into Ks. All these values we have already calculated in step number 8 while checking for shear. B naught we had calculated, D we had calculated, sorry, Ks we had calculated. Okay, if I show, wait, where was this? This one in the step number 8, what we had calculated here, B naught we had calculated, B naught we had calculated here, this one, B naught we need here, we need VU we had calculated, all this are calculated already here, DU, this one, 0.5 tau C, this one, we have B naught, we have calculated effective depth, we know 165, Ks was 1, this one, Ks we had considered it to be 1 because it was greater than 1.211, so we had considered it to be 1. Then what is remaining? Nothing. B naught is 2060, yeah, so 2060, so we got our this one VUS. So once we got our VUS, we can place all the values here, right? We can place all the values here and we can find out the spacing between the stirrups for shear reinforcement. Okay, for the shear, we can provide the stirrups at a spacing of, after placing these values, what we got, 112.7, okay, mm. So 110 mm we have considered spacing. Okay. Now similarly, if we calculate for the second question, if I show you the second, this was the calculation or checking for shear. After checking, what we have done, we have provided the shear reinforcement. Now if I show you these, okay, in the second question which we had done, this one, in the second question where we had a drop and a column head, what was there again, if for that we check the shear, what will happen, we had please see your question number 2, okay, which we had solved in flat slabs there, so that, and continue this step number 8 and 9 for that particular questions. So now here if you see in that second question, I'm taking mind that this is the second question where we had a drop and a panel had sorry, a drop and a column. So you already know these things. Just now we had talked about the check for the shear d by 2, that is here you had given your effective depth to be 225 when you had a drop, the total overall depth was 225 in the second question with a drop and a column head. So what would be our b dash shear? If you see, our column was a circular 500 dia and we had calculated the square distance. Okay, square distance also we had calculated of the column head. This was this is our critical section. Okay, this is our critical section here, which was, you know, that it is d by 2 distance. This was your column head, this distance 880 mm. We had calculated in our question when we were solving, it was 880, the square that size of the column head, so this was 880, right? So now this was the column head, so we will calculate from here the critical, this is our critical section for the shear, which is d by 2, you know, from IS code page 57, you already know this thing, just now I showed you 57, this one the critical section, this is at a distance d by 2 from where the periphery of the column or capital head this. So this is your d by 2, that means 112.5, 112.5, 112.5 is your critical section here. So once you know this, you can calculate your V naught. Okay, what is your VU here? The shear force, how much? This was your factored load 18, and this is your dimension 6. was your dimension given to you of the panel. Okay, b dash is how much? B dash is this 880 plus this one 102.5, 112.5, 112.5. So it is 1105. Okay, this distance, this. So if from this, I think it was 6, your size was 6 meter. So from the 6 meter, which was from all the sides, it was same. It was a square panel of same size. I think it was not a longer and shorter span kind of thing. It was a same size, 6 meter into 6 meter. So from that size, if we subtract this portion, we will get our shear stress 626 kilonewton. Okay, and B naught is 4 B dash, because from all the sides it is B dash. Our critical section length is how much? 1105 mm. So 4 into that will give you your B naught. So the shear stress will be VU by B naught into D. Here VU by B naught into D. So from the IS code, So VU is 626. You already calculated. B naught we got to be this much. D is 225. The effective overall depth in this case. Okay. So you have calculated your shear. If we see, then what is our tau c dash? We know from our IS code tau c. We know from our IS code tau c is how much? Tau c dash, this one. Ks into tau c value we have to check. So Ks into tau c. Ks we know 0.5 plus smaller by longer. But then this is both same.